Hello, everyone, and welcome to day 9 of Kaggle's 30 Days of Machine Learning. And today is a very exciting day. Today, we are going to be doing some real machine learning modeling using Python. And today, we are going to use. So, I've scrolled through the tutorial once and I've seen that they have been using decision tree. So, I would totally recommend you to see my decision tree lecture that was published right before today's tutorial, today's walkthrough. And if you haven't seen that, it's going to be difficult for you to understand what's really happening. So we will be using pandas, but now there's a lot of things in machine learning that you should know about, and we can try, we can see like what they have been doing. So they are saying you choose the variables. We need a list of columns in the data sets, and that's done using column property of the data frame. So we are actually using pandas, but there's a few more things that you should know about when we are talking about machine learning. We are saying like, okay, simple machine learning models have two major things, X and Y, and X is your samples and features, and Y is target variable. So you can have X looking something like this. You have many rows or many different samples, and you have many different features. So F1, F2, and so on to Fn. So these are the names of the features or the columns of a CSV file. And you also have targets. So target can be something like this. This is Y, target. Most of the time this is represented by X, this is represented by Y. And here you can have many different formats. You can have targets where the values are in 0 and 1. So you either have a 0 or you have 1. You can also have targets in which you have 0, 1, 2, and so on. So when you have something like this, when you have only two targets, it's called a binary classification problem. So you have only two targets to take care of. When you have a number of targets, number of classes associated with it. So let's say these are the pixel values of a given image, and that's different breeds of dog. So when these are pixel values of a given image, and it's just to distinguish cat and dog, it's a binary classification problem. But when you have different breeds of dog or different breeds of cat, then you have a multi-class classification problem. So this is multi-class. Then there's also problems like where you have Y, which looks something like this. And in each row, you can have multiple classes associated to a label. So this one, this one, this one. These cases are called multi-label classification. Okay. And then you have same thing, but with many different columns. And here you have real numbers. All these are real numbers. So this is multi-column regression. And if you have only one column, this is a single column regression. One column with one float value in each row. Single column regression. Okay, so you have binary classification, you have multi-class classification. So binary classification, when one sample associated with one of the classes, and there are only two classes in the whole data set. Multi-class classification is when one sample is associated with one class, but you have more than two classes in the dataset. Multi-label classification is when one sample can be associated with one or more classes, and you have many different classes in the dataset. A multi-column regression is when you have float values in the target but not just one. You can have many different columns. And single column regression is when you have float value in the target, but you have only one single target to predict. So now we go back to the data set and we see what's happening here. So we imported pandas and we use pandas to read this melb_data.csv. And here, let's read the data set first and see what we get. So we have Melbourne data, and in the previous lecture we saw that this is a data frame. So data frame, just printed, it looks something like this. You have different columns, you have different rows. It gives you the total number of rows and total number of columns. It will hide some columns, so that's represented by 3 dots. I will just look at the first few samples, the first 5 samples, and here I have suburb, address, a bunch of different things. So if I have to just print the columns, I can do data frame dot columns, and this will give me all the different columns that are present in the data frame. Now all these columns are called features, and one of these columns can also be our target variable that we are trying to predict. So when we saw the intro to machine learning, our cousin was trying to predict the price of the house based on certain different features. So that's the same thing here. Let's say you have the price column, and the price column can become a target that you have to predict based on suburb, based on room type, distance, the date of building or the year of building the house, and things like that. Okay, so now it says the Melbourne data has a lot of has some missing values, and we saw that in the previous one. So when we did dot describe, if I do Melbourne data dot describe, what do I get here? So here in rooms I get count of 13580, but as I see, like, the building area has a count of 7130, year built has 8205. So there are some missing values in building area, there are some missing values in the year built, and so on. So now it says that we have some missing values, and missing values can be removed using dot drop na. So here I have Melbourne_data dot shape. It gives me how many rows and how many columns I have, and then I do Melbourne data equal to Melbourne data drop na x is equal to 0. If I do this, let's see what the shape is. So the best way to learn is to just keep printing stuff. So axis equal to 0 means rows. So it has dropped rows which have non values on it or missing data in it. So now I had 13,500 samples. Now I'm left with only 6,196. Okay, so that's what is shown here. Now now it says we select. There are 2 different ways to select a column. So here they have done Melbourne data dot price. So you can do Melbourne_data price. So this gives you prices of all samples. Let's run this one. Okay, Melbourne data dot price. So this gives you prices of all samples. Here you see the indices. So indices still go to 12,000, but you only have 6,196 samples. So it's because when we dropped NA values, we dropped the NA values, but we kept the indices same. So if you see here, some indices are missing. So 1, 2, then you don't have the 3, you don't have 5, and so on. So there are some missing value. 12208 is missing. 12210, 12210, and 12211 is missing. So you have some missing values, but if you check the length of this, it's going to be same 6,100 something. So this is one way of selecting a column, and another way of selecting a column is just doing dot price. But this dot notation is not going to work when you have space in the column name, obviously. So then you have to use square brackets and then use quotes. So we select the target variable and we say y is our target variable, that's Melbourne data or price. And then we select features. So now I've shown you how to select one column, but you can select multiple columns using doing something like this, Melbourne data. And then you have the square bracket, and inside this, if we have one single string, it selects that strings, that column. But if you have a list of strings, so price, price, and rooms, it's going to select multiple columns. So that's the difference, and that's something you have to remember. So when you want to select multiple columns, you use a list of strings. If you want to select one single column, you use one single string. And now you have these features. So they have already defined some features for you: the number of rooms, bathroom, land size, latitude, and longitude. And when we have to select all these features, we can just do Melbourne data, and inside this, list of strings, and that's Melbourne features. Okay, so now this is your new data frame, and this is your training data. So you have selected the target variable, which is your price. You have selected the training data using the features that they have provided to you: room, bathroom, land size, latitude, and longitude. And based on these features, your job is to build a model to predict the price. Okay, so let's capture all this data in a new variable called x, as I showed you before. And now you can do some data exploration. So like x.describe, you see like none of them have any missing values. All of them have the same count. So this was one of the useful tricks we did, but we also lost a lot of samples. So how to handle missing data is something that we are going to learn in very near future. If you do x.head, so you do data.head, you see only the first few samples. Don't worry about the indices because we have dropped index 5. We have so it doesn't appear here. So otherwise we have 1, 2, 3, 4, 5. Now we have 1, 2, 4, 6, 7. So index 3 and index 5 has been dropped because they had NaN values in it. Now to build a model, see the previous video, learn about decision trees, and then come to this part. So to build a model, we use a very, very popular machine learning library called scikit-learn, and scikit-learn has a bunch of models built in, so you can just use it off the shelf. So here I do from scikit-learn, from sklearn.tree, import decision tree regressor, because it's a regression problem. You're predicting a value, you're not predicting a class. So that's why we import regressor. Otherwise we import decision tree classifier. And now we define our model. So my model is decision tree regressor, and inside that we have random state. Forget about it. So it's just a seed. So random state just ensures that every time you run the model, you have the same result. But in the beginning, you don't need to care much about it. You should, however, go for reproducibility of your machine learning models whenever possible. So now we define the model, and if we print the model here, so I have Melbourne model, and let's see what it says. So it's a decision tree regressor, and if you do help Melbourne model, it will tell you everything about it. Okay, but we have already studied this in my previous special video. So now I scroll down, and now what I'm going to do is I'm going to fit the model to my data. So my data is X, my target is Y. So let's just do Melbourne model.fit X, Y. It's going to take less than a few seconds. And then what you can do is you can make predictions using your model. So I have fit my model on all of the data I had, and I can do model.predict X. So it's now, sorry, it should be Melbourne model underscore predict and X. So now it's going to give me prediction for everything I have in X. So what do I have in X? So if I do x.head, these are the values that I have, and here I can do x.head too. And these are the predictions it makes. Now let's look at the actual values. So if I do x.head or if I do Melbourne data.head, it's the same thing. So here I have a lot of different things, but now I see there's a price column, and this is 103, 1035, 000, 1014 something, and 160 something, 1876, 1636. So now I trained the model on the training data, and I predicted the model on the training data, and it gives me like really nice predictions. Isn't that amazing? You're getting like the exact values from the model, and this is not good. So here they do the same thing. So they print x.head. So this is x.head, and for each row, you predict what the price is. Given this row, this is a price. Given this row, this is a price. Okay, now it tells you, okay, now you can go to the model building exercise. So we can go to the model building exercise, or we can go to the tutorial part 2. So let's do tutorial part 2, or okay, let's do the exercise first. So we do the exercise first. We are in the exercise and we import pandas as PD, and then we have some file. So they provide you with the file path and they ask you to read the data. So you can read it using pd.readcsv. And then there is some learning stuff from Kaggle, which you can safely ignore at this time, but you need to run it. So when it says setup complete, you move to the question. So the first step, the first question is select the target variable which corresponds to sales price. Save this new variable to Y. You will need to print a list of columns to find the name of the column you need. Okay, so here we don't know what the price column is. So I will just do home data. It has a lot of columns. Some are hidden. It has 1,481 columns. It has 81 columns. Wow. So I do dot columns and I added the brackets, and that's why it gave me the error. You don't add the bracket. And now there's so many columns, and I guess the column that we are looking for is the last one, called sale price. So I can do y equal to home underscore data dot sale price, or I can also do home underscore data sale price. Both are correct. So I will just write it here. So we got lucky, it was the last column, otherwise we had to look at all the 81 of them. But yeah, they don't make exercises, which will be very difficult for you. So we got the y variable, that the target variable, and now we create x. So it tells you create x, create data frame x holding the predictive features. So the features from the data that you would like to use to predict the sale price. And since you want only some columns from the original data, you first need to create a list with the names of the columns you want in it. So here it tells you, okay, we want to use these columns. Okay, so that's not a problem. I will create a list. Okay, I will create a list. I will cut this. I will create a list. And here, by just copying this part here and adding a square bracket here and adding a square bracket here, and then we can add quotes. So they are giving you the column name, so they are like feeding you like which columns you have to use. So these are some of the columns. I don't even know what these columns mean. Some of them are like very cryptic, but okay, no problem. We have this one, we have this one, we have this one, we have this one, this last column, and yeah, you need to take care of the comma. So I don't know why it appears like this, but now you have the data, which is home underscore data, and you can just do feature names. Sorry, feature names. So I might be missing something here. Comma. Okay, so I'm missing one quote here. Okay, so that's what you need to take care of. So you define the column names that you want to use as features, and then you can just choose the column names, because since it's a data frame, so you can just do some data frame, square brackets, list of strings. Now let's check the answer. So that's correct too. Before building a model, let's take a look at X. Okay, so it says, okay, let's look at X. So print, so we can do it differently. So like here we just write X, and yeah, okay, it gives you lot area, year built, blah blah blah, bedroom, whatever. Yeah, so some are cryptic. I don't even understand what they are, but you can also do describe, and if you should have some knowledge about the domain, and they will give you what these features mean. So you should know what features mean before you use them, right? So all of them have 1460 values, so we don't have any missing data. It gives you the mean, standard deviation, 25th percentile, 58th percentile, 75th percentile. It gives you the max value of each feature. So you got everything that you need. So now what do we have to do? We have to predict one value, one single column value. So we can just do from sklearn.tree import decision tree regressor. And your model here is decision tree model, decision tree regressor. You can specify some random state if you want. Random state is totally up to you. You can choose anything you want. Equal to 42. It just means that whenever it's generating something random, it's going to use 42 as seed. So you will always get the same results. And then I do Iowa model dot fit. So I fit the model on training data with the target variables. It's X and Y. And that's it. That's done. Now I make the prediction. So it's telling me make predictions with the model's predict command using X as the data. So we trained on X, and we are also making predictions on X. So predict X, and it's going to print me some predictions, and that's it. Now it tells you think about the results. So now when we think about the results, we can do X dot head. So and we can also do, so we can do print X dot head. We can also do Iowa model dot predict X dot head. So looking at only the first few samples, and we can also do, when we are doing head, we are doing like only the first 5 rows. So we can also do Y dot head. Okay, so let's print this Y dot head. Okay, so here you got X. Here you got X from here to here, and this is your Y. So these are the real values that you had in the dataset, and these are the values that you predicted. So, oh my God, this is like $1 million model which can predict exactly what the real value is, right? That's what you would think, that machine learning is so good. But think about it. Why is it so? And the answer can be found in the next part of today. That's model validation. So you have built a model, but how good is it? How do you quantify your model. You say like, okay, I will calculate the error. So I will take this sample and I will subtract this sample. I will calculate absolute error, and I will take the absolute value of this minus this, plus this minus this, plus this minus this, plus this minus this, and this minus this, and I will take the mean of it. So if you do that, you will see like all these values are same. So your original target is the same as what you predicted using your model. You don't have any kind of absolute error, right? That's called mean absolute error. You don't have any error at all. Your model is perfect. It's out of the world. But that's not a good model because let's see in this lecture. So because you didn't care about model validation, you validated the model, but you validated your model on the same data it was trained on. And when you do that, your model is going to learn your data perfectly, and it's going to give you perfect results. So many people make a huge mistake when measuring the predictive accuracy. In our case, it's error, since we are talking about regression problem, and they make predictions with the training data and compare those predictions to the target variables in the training data. And that's what we did. And that's not how it should be. So here they are also talking about mean absolute error, called MAE. So error is the actual value minus the predicted value. And you take absolute of it and calculate the error for each and every sample, like I showed you before, and then you take a mean of it. That's mean absolute error. So now they are doing all these things that we did in one given cell. So we can just run it, and it gives you the trained model. So once we have the model, we can calculate the mean absolute error. So for calculating mean absolute error, there is also a function in scikit-learn. So you can do from sklearn.metrics import mean absolute error, or you can just calculate it on your own. So you can say mean absolute error. So let's call it, let's give it a different name, MAE. And here MAE should take the true targets. So that's y true and y underscore pred. So y underscore pred is something that your model has predicted. So since these are numpy arrays, I can do a very simple thing. I can do return np.abs y underscore true minus y underscore pred. And I can divide this whole thing by the length of y underscore true. That's your mean absolute error. You can also do it using loops. You can go through each and every value in y true, each and every value in y pred, and you can subtract the corresponding values, take the absolute of each value and divide by the total number of values you have in y true or y pred. They must be the same. So we did this. And now here it gives us mean absolute error. So let's print our own MAE and see if that is the same. So mean absolute error. So this one has been printed using scikit-learn. And here I just do MAE and it gives me an error that NP is not defined. So obviously one thing I forgot to do is to import. So what is NP? It's numpy. Import numpy as np, and then we try to run this again and then see if we get the same value. So one thing that we forgot to do here is we also need to take the sum. So I can just do np.sum, np.absolute, and then we divide it by the length of y true. So now let's see. So now we get the same result. So we have implemented our own function for calculating mean absolute error. We have used numpy. You can use loops if you want to, but this is like one of the ways. Otherwise, you can just use the metrics from sklearn.metrics, and here you import mean absolute error. So we calculate the home prices on the full data set. And we calculated error using the scikit-learn function. We calculated the error using our own function. So now it talks about something called in-sample scores. So what are in-sample scores? It's not very difficult to understand, and don't get yourself confused. So let's say these are, this is your data that looks like this. You have a bunch of samples and you have a bunch of features, and here is your target variable, y. So if you take all of your data and you train a model, so this is your model which is trained. Here in our case it's decision tree regressor. You take the model and then you run the model on the same data set and you create predictions y hat. So these are your predictions. It's called in-sample. So the scores that you will get here will be in-sample scores. That's it. So the model, if the model is used to predict on the same data it has been trained on, it's called in-sample scores. And we should never do that. Whenever we do that, so like here it says my mean absolute error for each sample is 434. So my model is so accurate that it can predict with an accuracy of less than $450 for each home. So the price for each home, it can predict with such huge accuracy, right? I wish my model was so accurate. So what we do instead is we take the data. So this is our data set. And these are our features. So we take the data and this is sample 1. This is sample 2 and so on. You have n samples, like 1000 something in our problem, and you have features 1, feature 2, feature 3 and so on, fn. And here you have y, and y also have the same number of samples. So I'm just extending this. This is your target. So now what we do is we pick some samples. So we pick this sample. We pick this sample. Maybe we pick this one, the one next to it. Maybe we pick this sample, and I denote it with blue color, and this sample here is with green. This is green. Okay. So now I have given two different colors, and that's because I call these samples as validation data. And the blue samples are called, so this one, this one, this one, and this one is training data. Okay, so now when we build a model, we will be training our model only on the validation, only on the training set. And when we are calculating the error, when we are making predictions, we will predict on the validation set, and then we see how it is. So imagine like you have a set of values, right? And in this set of values, you said, okay, this is training and this is validation. But so you train your model on this data set and you validate on this one. So one thing that you need to take care of with model validation is you're training the distribution of your target variables in training should be similar to the distribution you have in validation set. And you can create a validation set very easily using scikit-learn's train test split. So here, let's take a look at how many samples we have. In X, we have 6,196 samples. So what you can do, you can write, give me training part of X, validation part of X, and training part of Y, and validation part of Y. Do this import from scikit-learn.model selection import train test split. So you import a train test split and it gives you X, and you provide your data X and Y and some kind of random state. So this is like very similar to saying I have, so this is my, if I say I have train underscore X, which is all samples of 0 to minus 200 rows and all columns. So this is, I can say like so let me see what X is. So X is this. Oh, okay. So X is a data frame, and no problem. So I can just convert the data frame to numpy array. So I can say it's a numpy array, and then I can just index it. So take all the values from 0 to 5996, and those are my training data. And if I take all values from minus 200 to end, all columns dot shape, that becomes my validation data, and I have 200 validation samples. So you can do the split by hand if you want, but it's always good to do the split randomly. Choose samples that belong to validation data, choose samples that belong to training data, train your model on the training data and make predictions on the validation data, and then calculate your error or any metric. So here we create training data, we create validation data, we create training labels, we create validation labels. We use this function to split our training and training data and full training data and full training labels, and we just provide a random state. So if you don't provide random state, it's going to choose different validation data all the time. If you provide 0, it's going to stick to one kind of validation state whenever you provide 0. So now after this, you fit the model. So now let's take a look at this one first. So we run this, and now we see train underscore X, and how many samples it has? 4,647. And if we take a look at val underscore X, it has 1,549. So here, one more thing that you can provide is test underscore size, and let's say I want 0.1, so that's 10%. So now if I look at val underscore X, it gives me 620. And if I look at X, we had 6,196. So 10% of the data is your validation data, and rest 90% is your training data. So now you define your model again. You fit the model on your training data and your target variables. You get the validation predictions. So here you have val underscore X, and calculate the mean absolute error. So now when you calculate the mean absolute error, it comes around 283,000. So you see the difference between your $434 and 283,000 now, right? So that's why you should always split your data. Here we have shown you a way of splitting the data. So you take training data, you split it into training and validation, and you build your model on training and you validate on the validation data. So this kind of validation is known as holdout validation. You have only one validation data. And the technique that allows you to have multiple validation sets from training set is called cross validation, but we will learn about that in near future. So now we can improve the model, but now it's time to do the exercise. So let's take a look at the exercise that we have today. So it seems like in today's exercise, they have given you some code. So they have imported pandas, you have the decision tree regressor, you have the file path, you read the file, you create the target variable, you have some features, you create X, you train your model on the whole data set that you have, and now it's giving you first in sample predictions and actual values. So that's something that we have already done. So we see that actual values and first in sample predictions are same because your model is learning everything about your data. And now the idea is to create your own validation set. So you do from sklearn.model selection, model underscore selection, import train test split. And here you have training data, validation data, training labels, validation labels, and here you can write train test split. Training data is X and targets is Y and random state, maybe whatever, what you do. So now it says the training data had different rows than expected. Give it an argument random state equal to 1. Okay, so it's telling you that you must use random state equal to 1 just to verify they have the same samples that they have in the solution. Okay, no problem. So now we have to import from sklearn.tree, import decision tree regressor. So if it would have been a classification problem, you import decision tree classifier. And here I do decision tree regressor, and they're also saying random state equal to 1. Fit the model, okay, Iowa underscore model and dot fit. So fit the model on the training data, the training data train underscore X, and my target is train underscore Y. We fit the model, that's okay. Create your predictions. So Iowa model dot predict, and you predict on the val underscore X. And yeah, it creates predictions. So predictions look something like this. So these are the predictions on your validation set, and print the top few predictions. Okay, we have already predicted all the predictions. So val predictions, we can print top 10, print the top few actual prediction, actual prices. So actual prices is val underscore Y, and let's see. Yeah, so now you see the difference. 186 is predicted and 231 is the real value. So now you have to calculate the mean absolute error. They have already written the import statement for you. So you do mean absolute error. And here the first one is the real value. So real value is val underscore Y. And then you have the predicted value, validation predictions. And you calculate the mean absolute error. So what is a val MA? So it's around 29,000. It's a huge value. So now your task is to think a little bit about this and learn what other metrics can you use for regression problems. Look into some classification problems. Maybe you can try to use decision tree classifier on your own for the Titanic data we had. Look into the tutorial that I prepared about the decision trees, and let me know if you have any questions and comments. If you like this video, do like, do subscribe, do share with your friends, and see you next time. Goodbye.